Okay, hello. This is Calc BC, Unit 6B, Lesson 5, Integrals for Net Change. We'll take a look at the next slide here to get this started. So we've got a recap of the units so far. We have this idea that the final amount of something you're measuring is equal to a starting amount plus net change. Over the course of the first couple lessons, we converted that idea into a function. Here we see a capital F of X that allows us to plug in any X value we want and find an amount at that time, location, whatever it is that X represents. And we see to do that, we need some initial starting amounts. Here it's the A, comma, capital F of A that serves as the initial amount. The fundamental theorem of calculus, parts 1 and 2 that we've been learning, tie in closely to this idea, and we use it to help us work with these functions. Today we're going to look at a very common application sort of problem associated with these ideas. This is a really likely candidate for a future, near future AP problem. Um, in these problems, let's assume we do have a function for amount, a rate of change of amount as well. And the problem will typically ask you to look at a rate in as well as a rate out. So, for example, imagine a boat, a canoe that is leaking water, or rather taking on water. And as it's taking on water, the rider, like this guy in the picture here, is trying to get that water out of the canoe. We see the leak here that represents water coming in. We see the bucket bailing water out. So we would be very interested in the rate at which water is coming into the canoe, but also the rate at which he's able to remove it. Those rates both play a role in determining if over time the amount of water is going to be increasing overall or decreasing. If water is coming in faster than we're getting it out, the amount of water increases. Likewise, if the rate out is greater than the rate in, the amount of water is going to decrease. We're going to practice identifying some of the setups here. I would actually recommend you pause this slide and try to fill out this page on your own before you look too closely at my answers. See if you can figure out what each of these expressions on the left is going to represent. So I'll allow you to pause right now. Once you've unpaused here, we'll talk through some of the answers. S is the rate liquid is flowing in. It's a rate in from a shower head. D is a rate out of a bathtub via a drain over an interval A to B. Therefore, the integral from A to B of just the S, integral of the rate in, would tell us the amount of liquid that has flowed into the bathtub within our time interval A to B. If I were to only integrate d of t, the drain, the rate of rate out, we would find the amount of liquid that flowed out of the bathtub from the drain from A to B. When I put these two rates together, this is really the more powerful tool. This is what gives us a measure of the net change in amount. We're taking into account water coming in, but also water coming out. So this would give us the overall accumulation in the amount of water in total from A to B. The last few expressions here are talking about the amount more so even than the accumulation, because after all, this third integral here is really most useful if I also happen to know how much water was in the tub at the start. So if C is the initial amount, we would do C plus our integral of rate in minus rate out to find the new amount of water in the tub. at the time t equals b. And lastly, we turn this all into a function. Suppose we've got this y of t representing amount at any time t. We're going to be taking the initial amount c, integral from a to our variable upper bound of t, s minus d, now with a placeholder variable, and I'm using x for that. Okay. Um, let's put some numbers on that. Suppose we know initial amount is 2. The rate in is 5t. The rate out is secant squared. And we would say y of t equals this starting amount plus an integral from the starting time to whatever time I want of 5x minus secant squared x dx. On to the next page. Got really just one more example set here. This is a very important example for us. We do tend to see AP problems similar to this one just about every year. It's not quite the same as an accumulator. This one is more of a calculator task, typically, not always, but typically. And it does feature rate in, rate out. We also have a graph. The colors on the graph correspond to the colors of the equation. We're dealing with a music festival. The number of attendees, that's an amount of attendees, is a continuous function. They don't actually give us that function. We know the number of people at the start of the timer, and then we have rates in, rates out, the rate at which people are entering. It's a trig function, make sure you're in radians, and then the rate out as well. First question, how many attendees enter during this 7-hour time period? Well, to learn that, I would simply integrate the rate in. This being a calculator problem, I don't need too much work. I just have to show the proper integral setup. And then I go to n int. I get an answer. In this context, maybe we're rounding to a whole number. But don't take my word for it. This is good practice for you to check on your calculator that you're getting the same result here. So yeah, that's the part A. Part B, we are given the exact, or pretty close to exact, t-values of the intersections we see in the graph. That's going to be helpful. We want to find the intervals when the number of attendees is decreasing. Keeping in mind, we still don't have a function for number of attendees. Okay. Even if I can't see that function, okay, I still know that any function is going to be decreasing if its derivative, its rate of change, is less than 0. And I do have enough information to piece that together. The overall rate of change for the number of people would be equal to the rate in, h of t, minus the rate out, j of t. So I need to look for where h minus j is less than 0. Equivalently, that would be like saying h is less than j. Blue graph is less than the red one. And that's pretty easy to tease out from the graph here. I see from 0 to the first intersection, which is the 2.5, and then again from 3 up to the next intersection, which is about 4.831. So that's how I'm arriving at this interval here where I know the overall number of attendees is decreasing because the overall rate of change is negative. Okay, on to part C, and this is a bit involved, but also it's a very common task, so we want to get pretty good with this. We are asked to find a global maximum number of attendees. I know it's a global max because we're given an interval and simply said, let's find the greatest number for this interval. I also want to find how many attendees this is, and I want to show some kind of justification. What's especially tricky here, we are being asked to maximize a function that we were not given. Okay, so here's one of the rare instances where we might choose to present a new function, which means we have to give it its own name, that we can show to a grader and then go on to maximize that function. Um, as of the previous lesson, lesson 4, we now know how to put together an equation for a amount function. So first thing I'm doing here, I'm going to give this function a name for reference. I should pick a letter that hasn't been used yet in the prompt. There was an H, there was a J. Let's call this thing F. Okay, I'm going to let f of t represent the number of attendees at time t. Excuse me. And we know that the final amount at a designated time has to equal a starting amount, which was given, plus integral from the starting time up to whatever time we want. So we're going to go with 1000 plus an integral 0 to t. And we're integrating the rate of change. I have to consider the in and the out. So we're going to go with h minus j again. And I'm using a dummy variable in my integrand. I can't reuse t here. But yeah, this would be a function for a number of attendees. And now that we have it, we're going to find a maximum. Of course, we're interested in where the derivative of this function is either 0 or undefined. We're already aware from part B that the rate of change was h minus j. We can confirm that here. Thanks to the fundamental theorem part 1, I could differentiate this integral and get h minus j. And of course, integral of the 1000 is just a 0. Okay, so f prime of t equals h minus j. We'll set that equal to 0. We'll also consider where it's undefined. And yes, it is undefined somewhere. Look at the j function. That thing is not defined when t equals 3. So therefore, h minus j is also not defined when t equals 3. So 3 is one of my candidates. I'm also taking uh, the same intersections we looked at in part B. Where does h equal j? That's precisely where h minus j is 0, and those are going to be the intersections in the graph. So I'm pulling a total of 3 time values as candidates. And of course, I'm also going to consider endpoints at 0 and 7. Now, as you look at my work here, you can see I've already somehow been able to plug all these t values into my f function to evaluate and see for myself where is the number of attendees the greatest. It turns out it's happening at t equals 0. The 1000 was the highest number of the day. So that would be my answer. But you might be wondering, how was I able to evaluate these? Is there perhaps a calculator shortcut? And of course, there is. And there is more information about that on the next and the final slide. We are actually able to input this amount function, even with the integral and all. We're able to input that into our calculators in the y equals menus. Now, this presentation is going to show how to do it with the TI-89, but it could be done on the 84 as well. Okay. Um, so yeah, here we see the steps. We see some screenshots from the calculator. We're going to firstly input both of the rate functions. The rate in I put in Y1, the rate out I put in Y2. You have to find an ABS function in the calculator. Go to the catalog button, which is, where's catalog? It's right under the apps button, not too far below and to the left of the arrow keys on the 89. It's on second 0 for the 84. So you have to find the ABS function to do absolute value. But yeah, we can input those rather quickly into Y1 and Y2. And then we're going to go down to Y3 and instruct the calculator to do 1000 plus the integral of Y1 minus Y2. And you can see how that's typed in here. If you want to pull in the integral notation on the 89 as you define a function, well, you're going to use second 7. You can see the little integral symbol on your calculator above the 7. So I'm typing in 1000 plus integral symbol in parentheses. You can literally type out y1 parentheses t minus y2 parentheses t. And I am using a t as the dummy variable here, which is a little annoying because if you go back to the previous page, t is our primary variable and x was the dummy. But unfortunately, your calculator is designed where you have to use x as the main variable. So we just have to be really careful and know that in the calculator, we're swapping the t and the x, even though our work is going to show something different. So t becomes the dummy, y1 t minus y2 parentheses t, comma t, and then comma 0 and x. We can actually assign the variable x as a bound if we want a variable upper bound. So now you have your amount of people function programmed into Y3. If you go back to your home screen, you can literally type Y3 parentheses and then each of our 5 candidates into the parentheses and evaluate them very, very quickly without having to retype some complicated equations over and over. So I would recommend that you do that. TI-89 is pretty similar. You're going to go to y equals, you're going to put your rate functions into y1 and y2, and you're going to go over then to y3 and try to type in 1000 plus integral. To find the integral on the 84, you want to go to the math menu on the left side of your calculator and find function integrate, which is choice number 9. And you're going to manually then, the 84 is nice. It shows you integral notation. So you're going to type in same things we just did, the 0 and the x for your bounds. I believe you can type in just y1 minus y2 inside the parentheses there on the fly. I'm trying to do that right now. To find y1 and y2, you have to go to the vars button just below the down arrow. Scroll over to y variables, hit the function tab, and then it'll show you y1 and y2. I'm doing it right now, and it seems to have worked. So, try it out. If you run into an issue, let me know. If it's not working, I'm sure you can Google the way to do it, or let me know in class. So yeah, we can input these functions pretty quickly in the calculator, and then we go back to the previous page, and this is where I've found all these lovely values of f of t that I ultimately use to answer the question. If you have any questions on today's video, feel free to reach out via email or come in and see me early in the morning. I'll be around to answer questions during class. I think on Friday we might have some time as well. Thank you for watching. Goodbye.